In the previous video, we saw three types of matrices: diagonals, rotations, and symmetric. We also saw that symmetric matrices can be composed using diagonal matrices and rotation matrices. Here we have reflections. So the FX matrix displayed here has an effect of reflecting as if there was a mirror placed along the x coordinate direction in this example. This is a related new visual. So the requirement that we have is to reflect across a mirror that is placed at an angle. So we achieve that using composition again. First we rotate, reflect, and rotate back. So let's come to the main idea. So given any matrix, it's possible for us to compose them using orthogonal transformations like rotations or reflections. We also need diagonal matrices which will be used for the scaling, either the shrinking or the stretching. So with that, it is possible for us to compose any matrix. That is the main claim. And that process is called as a singular value decomposition. So what is there in the screen, basically it talks about symmetric matrices and asymmetric matrices. So in symmetric matrices, it is showing R lambda R transpose. The lambda there is a diagonal matrix. R and R transpose are rotation matrices. We don't really need reflections to represent symmetric matrices. This form works. For asymmetric matrices, we will use a U or a V, and sigma here is again a diagonal matrix, and U and V are orthogonal transformations, and they have rotations and or reflections. So this is a form in which we are able to compose matrices. So how is this relevant to AI and ML? So basically, in one of the things that we do is mean square error computation. So the mean square error tells how far away, how much is the error from the required solution. The singular value decomposition basically tells us the magnitude and the direction of the error. So that is where actually this ties. So the singular value decomposition, the diagonal values that we get, as well as the orthogonal directions of U and V. So those are useful information that allows us to understand the direction in which we will be minimizing the error. In the next video, we will look at asymmetric matrices. In addition to singular value decomposition, we will also look at eigenvalue decomposition. So the eigenvector directions and the orthogonal transformation directions are the same in symmetric matrices, but they are not the same in asymmetric directions. So we need to basically, it helps us to understand where the change happens, so what brings that, and what eigenvalues and eigenvectors mean. So we will cover asymmetric matrices and the intuition around eigenvectors and eigenvalues in the upcoming video. Thank you.